say about Chapter 9. One is magnetic properties. We have something called paramagnetic, which is here. Paramagnetic has unpaired spins. That is, in manganese we have the half-filled D shell. All these are unpaired. We can actually measure how many unpaired spins there are in an atom, and thus confirm experimentally the electron configurations like this. Paramagnetic materials, the way we can measure that is because they're attracted to magnetic fields. Something called the Gouillet balance. So this would be paramagnetic here. This is paramagnetic. Anything with unpaired electrons is paramagnetic. Oops. Diamagnetic materials have all paired electrons. No examples here, but you know, neon, everything's paired. Chloride, everything's paired. Sodium atoms, paramagnetic. Magnesium is everything's paired in magnesium, so it's diamagnetic. Diamagnetic materials are weakly repelled by magnetic fields. Paramagnetic materials are attracted to magnetic fields. And so here's a summary of the properties here. The radius gets smaller, bottom left, bigger, top right. Ionization energies, highest top right, lowest bottom left. Metallic character, the most metallic element, cesium. The least metallic would be fluorine or neon or helium. Depends on how you define non-metallic. Because non-metallic are more variable in that sense. And so we got that. All right, we can make some predictions based on periodic properties. So, for example, melting points. You know, sodium melts at about 100 degrees C. Cesium melts at about room temperature. We can see, you know, sodium's a lot smaller, the bonds are stronger. Cesium's a lot bigger, the bonds are weaker. And so we could use these periodic things to understand things like melting points, as well as other properties. If we look at the melting points for the third period, we see it peaks at silicon. What's special about silicon? Well, you know, silicon has an extremely high melting point. Very hard to melt the stuff. Whereas it's a lot easier to melt sodium, magnesium, aluminum, even phosphorus, sulfur, chlorine, argon. You know, chlorine's a gas. The melting point is very low. Argon, you know, sulfur is a solid. The melting point of that's beyond. But silicon, what's special about silicon? What we have with silicon here is we have 4 valence electrons. In other words, it's halfway. In other words, here for silicon, we'll see this later, but there are going to be 4 unpaired electrons. Here, we're just going to, well, when we have this, well, actually, I shouldn't say this yet. We have 4 valence electrons. When we have 4 valence electrons, then we have the capability of forming 4 bonds. You know, with 3 valence electrons, like or 5 valence electrons in phosphorus, we can form 3 bonds. Sulfur can form 2 bonds. Chlorine can form 1 bond. Argon forms 0 bonds. And so here we go from 0 bonds to 1 bond, 2 bonds, 3 bonds, 4 bonds. Now aluminum is going to form 3 bonds, 2, 1. And so it's based on that. These do different things. These lose, these gain. All right, so there's some periodic properties in there. You can look at some of the chemistry of the elements here. Okay. The last thing we're going to look at here are the metal oxides versus non-metal oxides. Actually, let's do it over here. CO2 is metal oxide, or non-metal, actually, non-metal oxide. CO2 is a non-metal oxide. Non-metal oxides are acids. And so CO2 plus water, this is a Lewis acid-base reaction, forms carbonic acid. Metal oxides, like calcium oxide, are bases. So calcium oxide plus water forms calcium hydroxide. Semi-metal oxides are amphoteric. And they react either with acids or bases. And so aluminum oxide is amphoteric. They can react with acid or base. Although aluminum oxide is very unreactive in general. This has got very strong bonds, +3 ions, very strong bonds. And so you can look at the end of this chapter. And this chapter has some interesting stuff about the chemistry of the elements. So today what we're going to do is Lewis structures. So we've got to remember how to draw Lewis symbols. Lewis symbol for sodium, you could write as sodium with a dot, or sodium with an X if you want. X's or dots. I'll just use dots here. Sodium has 1 valence electron, chlorine has 7 valence electrons. And so sodium loses that, and notice chlorine takes it. Chlorine's a good oxidizer. Chlorine takes that electron, and we form sodium chloride. The Lewis structure for sodium chloride looks like this, where chlorine now has 8 valence electrons in an octet. In covalent bonds, chlorine's not strong enough to take the electron completely. So hydrogen's a lot more electronegative than sodium. Ionization energy for hydrogen is a lot higher than sodium as well. And so chlorine tries to take it, but it can't completely take it off, and therefore we get a covalent bond instead of an ionic bond here. Well, what we're going to do is we're not going to look at the bonding just yet. Later on we'll look at the bonding. Right now we're just going to look at drawing Lewis symbols and Lewis structures. Do you guys recall how to draw Lewis structures? This is reactivity here. Magnesium is 2 valence electrons. To react with 2 chlorines to form magnesium chloride. Aluminum is 3 valence electrons. Form Al2O3. Reaction. Usually the oxidizer pulls the electrons off. Because aluminum just doesn't give up 3 electrons, does it? It doesn't give up the 3 electrons because this can cost you a lot of energy. I1, I2, and I3 combined is going to be pretty big positive energy. And so normally when we think about the attack, it's the electron poor species pulling the electrons off. Electron richer species. All right, so we have different bonds here. Why do bonds form? Why bonds form is because it lowers the energy. And so molecules in general are more stable. If a molecule isn't more stable, then a bond wouldn't form. And so this is about bond formation, about polar and non-polar. We'll talk more about this later. But what we're going to do now is just try to write Lewis structures. And so do you guys remember how to do Lewis structures? Come up with a skeleton. First you count the electrons, then come up with a skeleton. Complete the octets, the peripheral atoms. Leftover electrons go in central atom. And so we'll jump ahead here and get through this. So this is the procedure for doing this. There's more to it, the procedure, than just this. And we'll talk about some of the subtleties. And so for the remainder of the lab period, which isn't that much, you're going to start drawing the Lewis structures for experiment 8 and the Lewis structures for experiment 9. Okay. Here's a refresher on drawing the Lewis structures. And then we'll talk about some of those as we go along, because some of those are more complicated. Okay. All right, so why don't you go ahead and start that